Continuity is another important concept in the discussion of differentiation because differentiability implies continuity. It means to say that when a function is differentiable at a certain value of the independent variable, it is also continuous at that particular value. Here's the definition of continuity. So if we say that the function f is continuous at x equals a if the following three conditions are satisfied. That are number one, f of a exists or it is defined. Secondly, that the limit of f of x as x approaches a exists. Okay, so we can say that the limit of f of x as x approaches a exists if both the limit of f of x as x approaches a from the right and from the left both exist and both are equal to the same number. Okay, and thirdly, if f of a is equal to the limit of f of x as x approaches a. So otherwise, we say that the function is discontinuous at x equals a. So meaning if one of the three given conditions is not satisfied, then we say that the function is discontinuous at x equals a. Now, how do we show that a function is continuous at x equals a? We just have to satisfy all the three conditions given. So, for example, in number one, we want to show that f is continuous at x equals 2. Now, we define f in this way. So, f is equal to x squared minus 4 if x is less than 2. It's equal to 0 if x is equal to 2, and then 4 minus x squared if x is greater than 2. So we are already saying in this example that f is continuous. So we just have to show by satisfying all the three conditions. So since we want to show that it is continuous at x equals 2, then a is equal to 2 in this case. So first condition, we want to show that f of 2 is defined or it exists. What is f of 2? In the second condition, if x is exactly equal to 2, the value of the function is 0, so f of 2 therefore is equal to 0. Now in the second condition, we want to show that the limit of f of x as x approaches 2 exists. So we have to check both the limit of f of x as x approaches 2 from the left and the limit of f of x as x approaches 2 from the right. If they both exist and they are both equal to the same number, then we can conclude that the limit of f of x as x approaches 2 exists. Now, when we want the limit of f of x as x approaches 2 from the left, then we take the limit of the first function, x squared minus 4. So as x approaches 2 from the left. Just because whenever x approaches 2 from the left, it means that x is a number less than 2. So we take the first condition, therefore, we'll have, substituting 2 for every x in the function, we'll have 2 squared minus 4, and that's going to give us 0. Okay, so when we want the limit of f of x as x approaches 2 from the right, it means to say that x is a number greater than 2. So we want the third condition and take the limit of the third function, 4 minus x squared, as x approaches 2 from the right. So substituting 2 for every x in the function, we'll have 4 minus 2 squared also equal to 0. So since these two are equal to 0, we say that the limit of f of x as x approaches to exist and is also equal to 0. Now, we'll be able to satisfy the third condition because as we have shown, f of 2 is equal to 0 and limit of f of x is as x approaches to is equal to the same number. So therefore, we have satisfied the third condition. So our conclusion would be, therefore, f is continuous at x equals 2. Now, how do we show that a function is discontinuous at a certain number? We'll have the next example. So we want to show in number 2 that f is discontinuous at x equals 1. Okay, so here's how we define f. It's equal to x squared plus 2 if x is less than or equal to 1, and it's 2x squared plus 2 if x is greater than 1. Okay, to show that f is discontinuous, we just have to show that one of the three conditions is not satisfied, at least one of them. Okay. So in this example, a is equal to 1. in the first condition, we want to know the value of f of 1. F of 1. So 1 is in this set, in the first condition. So f of 1, we will be able to get the value of the function when x is equal to 1 by substituting 1 in the first function. So that is 1 squared plus 2, and we'll get 3. Okay. Now for the second condition, we want the limit of f of x as x approaches 1. We'll have to check both sides of 1. We'll take the limit of f of x as x approaches 1 from the left, and the limit of f of x as x approaches 1 from the right. Okay, whenever x approaches 1 from the left, it means to say that x is a number very close to 1 but less than 1. So we'll have to take the limit of the first function, x squared plus 2, as x approaches 1 from the left. Okay, just because x is less than 1 in this case. So substituting 1 for x in the function, we'll get 3. Okay, now in the limit of f of x as x approaches 1 from the right, it means to say that x is a number greater than 1. So we want to take the limit of the second function, 2x squared plus 2, as x approaches 1 from the right. Again, substituting 1 for every x in the function, that's going to give us 2 times 1 squared plus 2, and it's equal to 4. These two are not equal, and so we say that the limit of f of x as x approaches 1 does not exist. So obviously, we will not be able to satisfy the third condition, but this is not important anymore, since in the second condition, we want this limit to exist, right? So if it does not exist, we don't need to check the third condition anymore. We can already conclude that, so therefore, f is discontinuous at x equals 1. Now we can classify the discontinuity of the function in two ways. Classifications of discontinuity. Okay, we have two classifications. One, it can be a removable discontinuity, and it can also be an essential discontinuity. Okay, when we say that the discontinuity is removable, we can always remove the discontinuity, redefine the function, and make it continuous. Okay, now the discontinuity is essential when the limit of f of x as x approaches a does not exist. So whenever the second condition is not satisfied, the discontinuity of the function at x equals a is always essential. When we will not able to satisfy the first and third conditions, then the discontinuity of the function is removable, provided that the limit of f of x as x approaches a exists. So here, if f of a does not exist or is undefined, okay, or the third condition, when f of a is not equal to the limit of f of x as x approaches a, okay, provided that this exists. Okay, so in the second example, f of is discontinuous at x equals 1 because the limit of f of x as x approaches 1 does not exist. So we say that the discontinuity is essential. Why? Because the limit of f of x as x approaches 1 does not exist. Okay, so therefore we cannot redefine this function anymore to make it continuous because the discontinuity is essential. Or we can say, when we say essential, the discontinuity is also said to be non-removable. Okay, number 3, we want to determine the values where the function might be discontinuous. Value or values, okay, where the function might be discontinuous. Test for continuity at those values. If discontinuous, classify the discontinuity. So we have to say whether it is removable or essential. Redefine the function if the discontinuity is found removable. Okay, we'll solve for a first. So in letter A, we will be checking if the function is continuous at x equals -1. A is equal to -1 here, just because of these conditions. Okay, so at x equals -1, the function might changes. Okay, so it might be discontinuous at that value. So if you want to check whether a function is continuous or not at a specific value of x, you just look at the conditions in the piecewise functions. So in the first condition, f of -1, what is f of -1? According to the function, whenever x is equal to -1, the value of the function is 4. So it is defined, or it exists. In the second condition, we want to check whether the limit of whether or not the limit of f of x as x approaches -1 exists. So we have to check the limit of the function at x equals -1 from the left, and also the limit of f of x as x approaches -1 from the right. Again, when x approaches -1 from the left, it means to say that x is a number close to -1 but less than -1. So we will be checking the limit of x minus 1, the first function, as x approaches -1 from the left. Substituting -1 for x in the function, we'll have -1 minus 1 and get -2. Okay. Now when we want the limit of f of x as x approaches -1 from the right, we'll check the limit of the last function, x squared minus 3, as x approaches -1 from the right. And that's a -1 squared minus 3, and that's a -2. Okay, so these two are equal to the same number, so we can conclude that the limit of f of x as x approaches -1 exists and is equal to the same number also, -2. But obviously, we will not be able to satisfy the third condition because f of -1 is 4, and the limit of f of x as x approaches -1 is equal to -2, so these two are not equal. So therefore, our conclusion is f is discontinuous at x equals -1. Now, to classify the discontinuity, going back to the two classifications a while ago, the discontinuity is only essential whenever the limit of f of x as x approaches a does not exist. But in this case, it exists and it is equal to 2. So therefore, the discontinuity is removable. Continuity is removable. So when we say removable, we can make the function continuous. How do we do that? If only we can satisfy the third condition, so if only this f of -1 and the limit of f of x as x approaches -1 are equal, then we can conclude that the function is continuous at x equals -1, right? So what we can do is change the value of f of -1. So to redefine the function, f of x should be equal to x minus 1. If x is less than -1, it should be equal to -2 if x is equal to -1, and it should be equal to x squared minus 3 if x is greater than -1. So now this function is continuous. Okay, that's how we redefine the function. So now f of -1 is equal to -2. The limit of f of x as x approaches -1 is also equal to -2. And so we'll be able to satisfy the third condition and conclude that the function is continuous at x equals -1. Right? For letter B, for what values do we check the continuity of the function? The function changes at x equals -3 and at the same time at x equals +3. So we'll check whether or not the function is continuous at those numbers. So the solution would be separate for a equals -3 and also for a equals +3. Okay, so we'll do the first -3 first. So we'll check the value of the function at at x equals -3. Okay, -3 is in the second condition. Okay, because in the second condition, x is in between -3 and 3. but not including positive 3, okay, in that condition. So we want to check the value of the function at x equals negative 3. We'll substitute negative 3 in the second function. So that's square root of 9 minus negative 3 squared. So that's square root of 9 minus 9, we'll get 0. Now for the second condition, what is the limit of f of x as x approaches negative 3? So again, we want to check the limit of f of x as x approaches negative 3 from the left, and the limit of f of x as x approaches negative 3 from the right. So from the left of negative 3 are the numbers less than negative 3. So we'll want the limit of x plus 3 squared as x approaches negative 3 from the left. That is equal to negative 3 plus 3 squared equals 0. Okay. Now when we want the limit of f of x as x approaches negative 3 from the right, we'll have to check the limit of square root of 9 minus x squared as x approaches negative 3 from the right. Because whenever x approaches negative 3 from the right, x is a number greater than negative 3. So that's a square root of 9 minus negative 3 squared, also equal to 0. So we say that the limit of f of x as x approaches negative 3 exists and is equal to 0. And the third condition will be satisfied because f of negative 3 is equal to 0, and it is equal to the limit of f of x as x approaches negative 3, which is also equal to 0. So therefore, we conclude that f is continuous at x equals negative 3. Now we'll solve for a equals 3. First condition, what is f of 3? To find the value of the function at x equals 3, we'll use the third function because 3 is in this set. Okay, so it's 3 minus 5. It's negative 2. Okay, now what about the limit of f of x as x approaches 3? Okay, of course we have to check both sides of 3. Limit of the function as x approaches 3 from the left, and the limit of f as x approaches 3 from the right. Okay, from the left of 3 are the numbers less than 3. Okay, so we'll have to check the limit of square root of 9 minus x squared as x approaches 3 from the left. It's going to give a square root of 9 minus 3 squared, or 0. Now what is the limit of f of x as x approaches 3 from the right? It is the limit of x minus 5 as x approaches 3 from the right. Okay, so that's going to give us 3 minus 5 equals negative 2. So these two numbers are not equal. So we conclude that the limit of f of x as x approaches 3 does not exist. So again, we don't have to satisfy the third condition anymore because we have not satisfied the second already. We can right away conclude that f is discontinuous at x equals 3. Okay, so the function can be continuous at one value of x and at the same time discontinuous at another value. Okay, so since the limit of f of x as x approaches 3 does not exist, we classify the discontinuity as essential. Discontinuity is essential. So we will not be able to make redefine the function and make it continuous anymore.